Question 7, Part B. The graph shows the velocity dx dt of a particle as a function of time. Initially, the particle is at the origin. Part 1. At what time is the displacement, x, from the origin a maximum? dx dt represents the velocity of the particle, and any part of the graph that is above the x-axis means the particle is moving forwards. Any part of the graph below the x-axis means the particle is moving backwards or in reverse. Any points on the x-axis means the particle is stationary or at rest. So we can see that between time t equals 0 and t equals 2, the particle is moving forwards. At time t equals 2, the particle is stationary. So from the graph, it can be observed that the particle is moving forwards in the interval t greater than or equal to 0 and less than 2, since the velocity dx dt is greater than 0 or positive. The particle is at rest at time t equals 2. Therefore, the particle's displacement is maximum at time t equals 2. Part 2. At what time does the particle return to the origin? Justify your answer. Since we have the graph of the velocity of the particle with respect to time t, the signed area bounded by the curve and the time axis t gives us the displacement of the particle, which represents the distance away from the origin at that point in time. So what we're looking for is a value of the signed area equaling 0, in other words, the area above the t-axis plus the area under the t-axis, since one is positive and the other is negative, cancelling out perfectly to give us 0. So when the particle is at the origin, the displacement is 0, which means the integral of the velocity dx dt from 0 to t equals 0. And we want to find this value of t here. From the graph, this occurs at time t equals 4. So going back to the graph, so t equals 4 is somewhere here. And we can observe that the magnitude of the area here and the magnitude of the area here up to time t equals 4, it's identical but opposite in sign. We have positive area, negative area, adding those together gives us 0, which means the displacement of the particle is 0 at time t equals 4. And I've written that here using integrals. Since the integral of the velocity from t equals 0 to t equals 2 plus the integral of the velocity from t equals 2 to t equals 4 equals 0, therefore the particle returns to the origin at time t equals 4. Part 3. Draw a sketch of the acceleration d squared x over dt squared as a function of time for t greater than or equal to 0 and less than or equal to 6. Acceleration is the rate of change of velocity with respect to time. Analysing the velocity graph, we can see that from time t equals 0 to t equals 1, the velocity is constant, which means the acceleration is 0. From time t equals 1 to t equals 3, the velocity is decreasing, which means the acceleration is negative. And at time t equals 2, and this is a point of inflection, the velocity is decreasing at its fastest rate. Now from time t equals 3 to t equals 5, the velocity is constant, and that's shown with a horizontal gradient there. And from t equals 5 to t equals 6, the velocity is increasing, which means the acceleration is positive. And at time t equals 6, the velocity is increasing at its fastest rate. And that can be shown on the acceleration graph. So we can see here that from time t equals 0 to t equals 1, the acceleration is 0, and that's shown with a horizontal line here on the x-axis. From time t equals 1 to t equals 3, the acceleration is negative, and the acceleration is at its most negative at time t equals 2. From time t equals 3 to t equals 5, the acceleration is 0, and from time t equals 5 to t equals 6, the acceleration is positive.